Okay, I see the number plateauing, so I think maybe we'll go ahead and start. First of all, hello and welcome everyone to this very special pop-up science speaker lecture hosted by the Maria Mitchell Association. I am Dr. Regina Jorgensen, the director of the Maria Mitchell Observatory, and I'd like to thank you all for tuning in tonight and to help us celebrate the MMA's NASA Week. So we're hosting this special week of activities in celebration of the upcoming launch of NASA's next great space telescope called JWST that we're going to be hearing about tonight. Some of the other Maria Mitchell Association NASA Week activities include 2 public open nights. If you're here on Nantucket, come out to the observatory on Milk Street Extension, the Loynes Observatory, both tomorrow night and Friday night from 7 to 8:30 p.m. for an open night. And then on Saturday, we'll actually be giving away free science kits at the Hinchman Natural Science Museum on Vestal Street from 10 a.m. to 1 p.m. So head down there if you're interested in getting one of the free science kits. The kits include JWST swag, some educational activities, and an opportunity to explore the life cycles of stars with a bracelet making activity. And before I begin the introduction tonight, I'll just make one note on how we're going to run the program. I'd encourage you to ask questions if you have them, and please do so in the Q&A function, which you should find down at the bottom of your screen. And we will take questions at the end of the talk tonight. So any questions that occur to you, please go ahead and pop them in the Q&A. So it's now my great pleasure to introduce our guest speaker for tonight, Dr. Stephanie LaMassa. And Dr. LaMassa is a scientist at the Space Telescope Science Institute working on the JWST mission. Dr. LaMassa received her bachelor's degree in astronomy and physics from Boston University, and she then worked for several years as a mission planner for the Chandra X-ray Observatory at the Harvard-Smithsonian Center for Astrophysics right here in Boston. And she did that before starting graduate school at the Johns Hopkins University in Baltimore. After receiving her PhD from JHU, she held a postdoctoral research position at Yale University, followed by a fellowship position at NASA Goddard Space Flight Center. Dr. LaMassa joined the Space Telescope Science Institute in 2017 and currently serves as, as the manager of the JWST NIRISS instrument branch. Her studies are in the growth and evolution of accreting supermassive black holes, which are called active galactic nuclei, and the interplay between black hole fueling and star formation from a multi-wavelength perspective. Dr. LaMassa is also interested in understanding how highly variable active galactic nuclei provide insight into the feeding habits of black holes and their lifetimes. And tonight she's going to be talking to us about this next great space telescope and get us all excited for the upcoming launch. So just to conclude again, if you have any questions during the talk, please put them in the Q&A and we will take all of the questions at the end. And so at this point, I will stop screen sharing and turn that over to you. Thank you so much.
Okay, let's give this a go. Share that screen. And then press play. On the wrong screen is being shared. All right, I got to do it in the other order. Okay. Let me first play the display. And then do the screen share. Share screen. Just 2. I think you're still seeing the wrong one, right?
No, we can see it. That looks good.
Are you seeing the presenter view?
I do not. I see just the black slide with the title and your name.
Okay.
Yeah.
All right. So if that, because it's showing the screen that's being highlighted is a different screen than before. So if you end up seeing my note slide, just interrupt me and I will
do
fix
that.
it. Okay.
I will let you know. Yeah, it looks good right now.
All right. Excellent. All right. Well, thank you all for having me. And I'm very excited to talk to you all about JWST and what we're going to learn over the next year and a half. But first, I always think it's important to define terms. So let's start at the basics and describe what light is. Light is how those of us with sight, one of the main ways that we get to learn about the world around us. But if you were to ask a physicist, they will tell you that light is both a particle and a wave. And it's the wave nature of light that we're going to focus on. Because the wavelength, which is the distance between one peak to the next peak of a light wave, encodes a lot of information about the energy that is transmitted by light and what we are able to observe. The shorter the wavelength, the more energy the light has, and the longer the wavelength, the less energy the light has. And I picked these colors on purpose because blue light has a shorter wavelength than red light. And white light itself is made up of different colors. And we can see this when we see that light itself is refracted, whether that's through water droplets in our atmosphere, leaving beautiful rainbows, or whether it's through a prism. And the order in which we see colors is always the same. If you were like me and you learned about Roy G. Biv in elementary school, it's always the same order: red, orange, yellow, green, blue, indigo, violet. And those colors correspond to the wavelength of light. So they're always going to be in the same order. But all those colors that those of us privileged to see, it's just a small sliver of the electromagnetic spectrum. There is light at shorter wavelengths and more energetic. So light including ultraviolet, X-rays, gamma rays. And light with longer wavelengths, infrared, microwave, radio. Most of this light we can't see with our eyes, but the universe doesn't care. Everything from planets to stars to galaxies to the very seeds that create the universe that we see around us today emit light across the electromagnetic spectrum. So if we truly want to understand the universe and our place in it, we need to build telescopes to observe light that would otherwise be invisible to us. And as astronomers, we've done this for decades. We've built telescopes that have been able to observe light across the electromagnetic spectrum. And the NASA astrophysics flagship missions have done this as well. So these NASA flagship missions are these big, ambitious projects, these observatories that have been launched into space that have given us the most deepest views yet of the cosmos. So most people are probably familiar with the Hubble Space Telescope, which launched in the 1990s, and that observes visible light as well as some infrared and ultraviolet. And it's kind of just hard to understate the impact that Hubble has made to our knowledge of astronomy, fundamental physics. And the images and discoveries, I think, rightly fill many of us with a sense of awe and wonder. Hubble itself is just one of NASA's great observatories. And the other observatories are complementary because they observe other parts of the electromagnetic spectrum. So there's the Compton telescope, which observed the most energetic light, gamma rays. There's the Chandra Observatory, which observes X-rays. And Chandra has a special place in my heart because, as you heard in the intro, I used to work on the Chandra mission for several years before I started grad school. And the Spitzer Space Telescope observed infrared light. The next generation of flagship missions continue in this tradition, starting with JWST, which will launch later this year, followed by the Nancy Grace Roman Telescope, followed by, we'll probably find out tomorrow at noon when the results of the decadal survey are announced. So the astronomy field is all abuzz right now, waiting to find out what that will be. So JWST as a NASA flagship mission is being developed with our partners from the European Space Agency and the Canadian Space Agency. And its wheelhouse is to observe infrared light. And if you're curious about the details, wavelengths of light that JWST is sensitive to is between 0.6 microns to about 28 microns. So it's kind of shown in that orangey rectangle. And the discovery of infrared light is an interesting story. And like many discoveries, it starts with an observation. Well, that's kind of interesting. Let's investigate this further. Around the turn of the 19th century, William Herschel realized that colored filters seem to have different temperatures. So he set up an experiment to test this, where he took a prism to diffract white light into its constituent colors, and then took thermometers to measure the temperatures of those colors. And he found that red light was hotter than green light, and green light was hotter than violet light. He decided to repeat the experiment. And this time with a twist, he put a thermometer beyond where he saw red light and measured the highest temperature yet. And like he looked into this, he started switching out the thermometers just to make sure it wasn't something with this experimental setup. No matter what he did, he got the same result. What he was measuring beyond red light had the highest temperature. And he published a paper in the 1800s where he noted that it's evident that there's a refraction of rays coming from the sun that are not fit for vision, but yet are invested with the power of occasioning heat. He termed this light calorific rays, which we now refer to as infra or beyond red. Observing in the infrared gives us a unique view of the universe that we can't get at other wavelengths. And one of the ways that it gives us this unique view is something that William Herschel was starting to touch upon in the 1800s. Anything that gives off heat gives off light. And where on the electromagnetic spectrum that we give off light depends on the temperature of that object. So hot objects will give off most of their light at shorter wavelengths, while cooler objects will give off most of their light at longer wavelengths. So for example, the sun is at about 5,500 Kelvin, so its peak wavelength of light is right in the visible range at 0.5 microns. So it's not surprising that our eyes have evolved to observe visible light. Humans have a much lower temperature than the surface of the sun, luckily. And we have temperatures at about 305 Kelvin or so. And that means that where we give off light peaks at a wavelength of about 9.5 microns. And this is how night vision goggles or cameras work. If you've seen those videos, if you've seen those pictures, those are cameras that are tuned to pick off light at wavelengths where living beings like humans or animals give off most of their light due to their body heat. So if we want to extrapolate this to the universe, using infrared gives us the ability to observe objects that we otherwise can't see in the visible. These could be things like cool stars that don't give off much light or visible light, objects like asteroids, which do a good job of reflecting light from our sun, but give off most of their energy at infrared wavelengths. Or what's shown here is an artist's impression of a brown dwarf, which are these objects that aren't quite stars, aren't quite planets. They're not large enough to ignite nuclear burning in their cores to become stars, but they're much bigger than just planets that we know of in our own solar system. Observing the infrared also gives us the ability to see through dust. So what's shown here is a gorgeous Hubble image of the Carina Nebula, where nebula is a cloud of dust and gas in space. And it's being lit up by these stars that are around it and that are kind of sculpting this nebula. Now, the wavelength of visible light is about the same size as the dust particles. So any of the stars behind this nebula, the visible light ends up getting scattered. And so we can't see behind it. If we were instead to look at the nebula in infrared light, infrared has longer wavelengths, so that allows us to peer behind the dust veil, revealing the stars behind it. And in particular, you can see that there's this bright star kind of in the upper part of the nebula that's shooting these jets on either side of it that we weren't able to see if we just had the Hubble image in the optical. And you can see how these two views give us the ability for a more complete picture of the universe. The infrared also gives us the ability to see the universe thanks to the Doppler effect. So an analogy of the Doppler effect is, let's say you're standing at a train station and a train goes by and it blows its whistle. As the train moves away from you, the tone of the whistle sounds lower and lower and lower and lower. And that's because as the train is moving away from you, that sound wave that's being given off by that train whistle is moving away. And that wave is growing to longer and longer and longer wavelengths. We know that the universe is expanding. And as it's expanding, it's carrying galaxies with it along for the ride. So as galaxies are moving further and further away from us in the expanding universe, the light from those galaxies, from the stars within them, which could start out at optical wavelengths, visible wavelengths, or oftentimes ultraviolet wavelengths from very young stars, travel through the expanding space, getting where the wavelength gets stretched, that by the time it reaches our telescopes here, we observe it in the infrared. So this gives us the ability to observe very distant objects like galaxies. So JWST will observe the infrared universe using 4 cameras, 3 of which observe near-infrared wavelengths, and 1 of which observes at mid-infrared wavelengths. So the near-infrared detectors observe wavelengths of light that have shorter wavelengths. If you want the numbers, it's between 0.6 to 5 microns, while the mid-infrared instrument observes light at longer wavelengths, between 5 to 28 microns. And I want to point out this little guy here, the near-infrared imager and the spectrograph, or NIRISS, because that is the instrument that I work for. I am the manager of the NIRISS team at Space Telescope Science Institute, where we're responsible for the science operations of NIRISS. NIRISS itself is a contribution from the Canadian Space Agency to JWST. So JWST is going to use these 4 science instruments to observe the infrared sky with the largest telescope ever sent to space, with a mirror that's 6.5 meters in diameter and made up of these 18 individual hexagonal segments. And these photos don't actually add anything new or interesting to the talk, but they may have a special place in my heart because these are photos that I took of the JWST mirror back when I was a fellow at NASA Goddard Space Flight Center. And at that time, the telescope mirrors and the instruments were being tested and put together at Goddard. And there's a viewing window that we could go to as they were working on the telescope and take pictures. So these are my photos of JWST from about 5 years ago. So observing the infrared sky is important, but it also comes with challenges. Because again, anything that gives off heat gives off light, and oftentimes that light could be at infrared wavelengths. So if you really want to be as sensitive as possible to infrared light from the cosmos, you have to keep JWST as cold as possible. So one way to do that is to have the orbit of the telescope to be as far away from the sun as you possibly can. So JWST is orbiting at this place in sky called the Lagrange point 2. And it's an area where the gravity of the sun and Earth and anything in that point will balance each other. So this point is far away from the sun, it's far away from the Earth, and it's far away from the moon. So that's one way to help keep the telescope cold. But JWST needs to be kept even colder still. And another way that we do this could be seen in this image where you see this kite-shaped shape beneath the telescope. And what that is a sun shield. And this really is a success of material science and engineering. It's this shield that is the size of a tennis court, so it's huge, and it's very strong and it's made of this ultra thin material. And there are these 5 separate layers, and it has this kite shape to it to deflect heat off to the sides. And each layer of the shield allows less and less heat through to where the telescope and the science instruments are. So that if you were to compare the hot side to the cold side of JWST, there's a temperature differential of 573 degrees Fahrenheit. So this works well for the near-infrared instruments. They could operate at what we call an ambient temperature of about 39 Kelvin or so is kind of what the prediction is. Might be 37 to 39 Kelvin. For the mid-infrared instrument, which again is observing longer wavelengths, it has to be kept even colder still. So there's a cryo cooler to drop the temperature for that instrument down to 7 Kelvin. Now remember, 0 Kelvin is as cold as you could possibly get. That's the limit. This is 7 degrees above that. Okay, so now we've been able to solve how to keep the instrument cold and how to make sure that JWST is really sensitive to observe as many infrared light as it can. You need the big mirror, you need the sun shield, but then you have this other challenge in that you need to fit it into a rocket that has a fairing of 16 feet. When the mirror itself is 2 stories tall and the sun shield is the size of a tennis court. So how do you do that? And the answer is that you fold it up like origami. And that works. It's difficult, but it works. But then this poses another challenge because then once it gets into space, it needs to unfurl. So these are just some of the things that make JWST very innovative as well as challenging. The Associate Administrator of the NASA Science Mission Directorate, Thomas Zurbuchen, wrote in an email to the JWST mission back in August, where he noted that Webb is the Apollo program of NASA science. This is the level that we're talking about for this mission. It's the largest telescope that's ever been launched into space. You have 4 science instruments. It's like getting 4 telescopes for the price of 1. You've got to keep the telescope cold. So you have to have an orbit where it's 1 million miles away from the Earth. You have to have this large sun shield to block as much light as possible from the sun. And also notice when you look at the pictures of the telescope, it's an open design. It's not closed in a tube like every other telescope we've ever seen, any other telescope we've ever seen in space or telescopes on the ground that have domes around them. And the reason for this is because the tube itself would release heat, which releases infrared light, which is a background. If we want to observe infrared radiation from the cosmos, we don't want it coming from our own telescope. And I actually have this picture of a lithograph from 1998, which shows different design concepts for JWST. Then you have to fold it up so it fits into the launch vehicle, and then it's got to deploy after launch. where each deployment has to go right. And there's about 50 of those. Compared to Hubble, JWST's older sibling, and a telescope that many of us love, there are some interesting differences. One is what the wavelengths of light that they're sensitive to. We've talked a lot about how JWST observes in infrared. Hubble observes in the optical, also has some ultraviolet capabilities, and a little bit of infrared capabilities. So there is this little regime where there's an overlap in the type of light that JWST and Hubble is sensitive to. Between those wavelengths of light are between 0.5 and 1.7 microns. But because JWST has more updated detectors and instruments, and it has a much larger mirror, and it can stay much colder, it's more sensitive in that overlap region than Hubble is. JWST has the larger mirror. The primary mirror for Hubble is maybe about 8 feet, a little bit taller, or I guess more than a little bit, a couple of feet taller than a person, compared to JWST, where that mirror is 2 stories tall. Orbit for JWST, much further away. Hubble orbits the Earth at an altitude of 570 kilometers. And again, JWST goes past the moon, about 1.5 million kilometers from Earth, which is about 1 million miles, a little bit less than that. So while Hubble has had multiple surfacing missions, partly at the beginning of its mission to correct a spherical aberration to make sure Hubble could get the crispest images ever. And then after that, to swap out science instruments. JWST can't be serviced. It's too far away. We've got to get this right the first time. And another difference between JWST and Hubble is that JWST can't be serviced. JWST has to unfurl in space. And that has a lot of complications. So for the past about 2-ish years or so, JWST was in Northrop Grumman in California, going through a series of tests. The telescope and the instruments were merged with the sun shield and the spacecraft bus, and then a whole bunch of tests were done over the years to make sure all the different components are working with each other. About a little bit 6 weeks ago or so, end of September, JWST was very carefully packed up, put on a boat, and then shipped, avoiding the pirates, going through the Panama Canal to arrive at its launch site in French Guiana on October 12th. It's gone through another series of tests while at the launch site, and now it's getting packed up to get ready into its launch configuration for its launch date of December 18th. And that's where the fun begins. Sometimes after launch, once you hit space, you could take a deep breath and relax and think you're done and just start taking science. Not for JWST. This is when we start having the complicated deployments and commissioning. So at 33 minutes after launch, the solar arrays deploy. This is what powers the spacecraft. And then that's then followed by the high gain antenna deployment, which is how JWST will communicate with the ground and send data to the ground. 2.4 days after launch, JWST will wave hi to the moon. All right, probably won't actually wave, but it'll pass by the moon. 2.7 days after launch is the deployment of the JWST pallets that hold the sun shield. So first, the forward pallet deploys, and then about 3 days, and then the second pallet deploys. 3 days after launch, the tower assembly extends, and this is important to create space between the telescope and the science instruments shown in the back there on the spacecraft bus. So they're moved away from each other, again, to make sure that there's not heat coming from the spacecraft bus to cause extra background for the telescope. 5.5 days after launch is deployment of the booms for the sun shield. First on one side, then on the other side. This is a little bit sped up. It goes a little bit slower in reality. Then full sun shield deployment. The sun shield is unfolded. The tension in the membranes increase. And then the 5 separate sun shield layers are separated from each other. 6 days after launch is when the secondary mirror deploys. I always get nervous watching this. This is what's going to focus light into the primary mirror. And then up to 9 days after launch, the side wings of the primary mirror deploy and lock into space. At this point, the telescope will continue to passively cool as it flies towards its orbit point at L2, Lagrange point 2. And it gets there about a month after launch. But we don't start the science program then. That's when we start commissioning for 30 to 180 days after launch. And that's where things get real for me and all the folks working on JWST instrument teams. 30 to 90 days after launch, we turn on the instrument, we do initial checkout, we focus the telescope. All those separate 18 hexagonal segments are going to show 18 different images that all have to be phased together into one image. 90 to 120 days, we do detector characterization and compare what we see in sky versus what we've measured on the ground in the cryo chambers. And then the last 60 days, things get really, really busy for us, where we take observations for every observing mode and do preliminary calibrations. So then we could finally answer the question that many of us have been waiting years to hear an affirmative response to: are we ready for science? So after commissioning is done, the science program begins. And there's a lot of science programs that are accepted for the first year of science operations. And I'm just really going to give an overview of just a handful of them, just to demonstrate how JWST is uniquely poised to make important discoveries from our own solar system to the edges of the universe. But this is just a sampling. There's much more that will happen that first year. We start in our own solar system with observations of Io. Io is the moon of Jupiter, which is the most active, volcanically active world in our solar system. There's an observation in the first year of science operations to study the volcanism on Io, particularly to look for these so-called stealth volcanoes that currently look like large hotspots, but with JWST's capabilities, we could resolve that into individual volcanoes and understand the effect that these volcanoes have on the atmosphere of Io. Moving beyond our solar system, we are going to study worlds around other planets, so-called exoplanets. And this has been a burgeoning field over the past 2 decades. When I started undergrad, there were maybe 1 or 2 possible thought exoplanets known, though it wasn't really, I'm not sure there was much confidence in those discoveries. And now there's over 1,000 that are known. And there's a lot that we're learning about exoplanets. So one thing that we want to know about these planets around other stars is to try to understand planets that might be around the same size of our Earth. particularly, some of these planets are orbiting stars that are these M stars that are very active. And there's a question about whether or not planets around those stars can retain an atmosphere as they're dealing with this barrage of radiation coming from these very active stars. And if we do detect atmospheres around these stars, we could then characterize them using a technique called spectroscopy. So here we wait for a planet to transit or orbit in front of a star. And when it does so, it will block out some light from that star. And the different layers of the atmosphere will absorb more light at some wavelengths than other wavelengths. So this is a way to probe that different atmospheric layers of the planet, as well as identifying molecules that will leave their signatures in the spectrum that we observe. And this will give us the ability to characterize these atmospheres and allow us to look for molecules that might be biomarkers. And this could give us a way to understand how perhaps even our own solar system came to be. We'll also be able to image planets around other stars, which is a very difficult thing to do. So if we're in our own solar system, we could see the planets that are here. But if we were to travel away from our solar system and then look back, we'll see that the planet gets lost in the glare of the sun. If we're able to take a mask and block out the light of the sun, then we could observe the planet. So we've been able to do this in some telescopes with a technique called coronography, where we could use a mask to block out the light from the host star and observe the planets that are orbiting around it. But there's only so much that we could do from the ground, and even from some of the coronagraphs that are on Hubble. JWST will revolutionize this, and this will be a way that we could directly detect planets that are otherwise invisible and learn more about planet formation. If we want to learn about how planets form and how our own solar system formed, it's also important to understand the star formation process. So there are observations to look at star forming regions within our own galaxy. What's shown here is a region of the Orion Nebula. And this is an area where there's a prodigious amount of star formation. There are these massive stars giving off lots of ultraviolet light. And it's true, JWST does not observe the ultraviolet, it observes the infrared, but you can also see there's lots of dust here. And a question that we have is to understand how this ultraviolet light affects its environment, how it breaks up molecules, how it ionizes atoms, how it heats dust and gas. And JWST will be able to allow us to study this in unprecedented detail. And this could also give us a way to try to understand the earlier universe, where regions like this were much more common. So all of these are examples of science that we're going to do at JWST within our own galaxy. And it's all cool stuff. But I'm an extragalactic astronomer. I study black holes in other galaxies, and JWST is going to do lots of really cool stuff here as well. So we know in the centers of probably nearly every massive galaxy, there lies a black hole that we call supermassive black holes. These black holes have masses that could be millions or even billions of times heavier than our own sun. And most of the time, these black holes are dormant, but in some cases, they could be actively growing by feeding on nearby matter. If matter gets too close to a black hole and can't escape its gravitational pull, it spirals down into the black hole. giving off lots of light and energizing its surroundings. And these processes impart observable signatures that we could use to identify galaxies hosting these growing black holes, both nearby and in the distant universe. And it also seems clear from observations that there is a link between these supermassive black holes and the galaxies in which they live, but what that link is not exactly clear. There could be a common mechanism that causes both to evolve contemporaneously. There could be cases where the energy that comes from the growing supermassive black hole could affect the environment in the galaxy itself, perhaps even shutting down star formation. And understanding what these various processes might be is an active area of study and has been for decades. One mechanism that could link the coevolution of these supermassive black holes and galaxies are galaxy mergers. So galaxies that can become gravitationally bound and orbit around each other and eventually collide can be a way that you could stir up the dust and gas in those galaxies, triggering lots of star formation while also funneling material to the center of the newly formed galaxy towards that black hole and turning it on and making that center of the galaxy active. And parts of this process does end up having lots of dust in the galaxy. And it does leave a strikingly beautiful image, like the one shown here. But the dust also kind of really gets in the way if you want to understand what's happening in the center of the galaxy. So this is where JWST could be very helpful, because it'll allow us to peer through that dust, observe the centers of these galaxies, and really study in detail how quickly these stars are forming, how much these black holes are feeding, and what the interplay between these two processes are. It can also give us a glimpse into our own future. Our neighboring galaxy, the Andromeda Galaxy, is on a collision course with us. So this may be what our future looks like, albeit a very distant future. It'll be 4.5 billion years before this collision happens. So these beautiful galaxies that JWST, these merging galaxies that JWST will observe within its first year of science observations are relatively nearby, and that's why we could see them in these stunning images in beautiful detail. JWST will also observe galaxies far, far away. And it will do this by doing surveys. So many people might be familiar with the Hubble Deep Field Survey from 1995, where Hubble just looked at a blank part of the sky that was smaller than the size of the moon and just stared there for 10 days. And what had been a blank piece of sky, we saw thousands of galaxies. Future generations of surveys with Hubble have gone deeper and deeper. So identifying and discovering galaxies further and further away. And the further away the galaxies are, the farther back in time you're looking. So the state of the art right now with Hubble is the Ultra Deep Field Survey that used the infrared camera on Hubble to observe galaxies that were in existence 400 to 500 million years after the Big Bang. So for reference, our universe is about 13.7 billion years old. So these are galaxies that are 0.4 to 0.5 billion years after that point. Okay. And this is as far as Hubble can see. Galaxies further away that have young stars giving off ultraviolet light, as that light travels through the universe to us, it's going to be shifted to infrared wavelengths that are beyond what Hubble is able to observe. But JWST will be able to observe those wavelengths of light. So JWST will be able to push the envelope further to observe galaxies 200 million years after the Big Bang. JWST is going to observe some of these famous legacy fields that Hubble and its sibling great observatories like Chandra and Spitzer also observed. And it will be able to discover the first galaxies, the first black holes, and the end of the cosmic dark ages. We'll understand what the first galaxies are made of, what their characteristics are, how big they are, how quickly they're forming stars, how massive these first generation of supermassive black holes are. And we could understand how both these galaxies and these growing black holes are energizing their surroundings. And this will be able to help us understand their evolution from their infancy to the present day. And maybe even understand how our own Milky Way galaxy came to be. So again, this is just a very brief overview of the first year of the science program. Even if I spent this full hour talking about the first year of science at JWST, I still wouldn't cover it all. And this is only what we know about what we'll discover. There's also bound to be discoveries that we can't even imagine now. And an example of this is that Hubble Deep Field image, the first one in the 90s. At that time, the Hubble director put his reputation on the line to observe a blank part of sky for 10 days. And what came back was absolutely stunning. Those observations are iconic. And now we can't even imagine having a large flagship mission that doesn't do these types of surveys. It's just become part of what astronomy is today. And what's that going to be for JWST? I don't know what that answer is, but I think that's part of what the excitement of the first year of science at JWST will be. So JWST is the most complex observatory ever built by humankind. And its infrared eyes will reveal the universe, both near and far, including studying geology and other bodies within our own solar system, characterizing other worlds and star formation within our own galaxy, and observing nearby and distant galaxies to understand their evolution and how the first galaxies and black holes came to be. The next year and a half will be an exciting one, so stay tuned to hear about what we'll learn and come on the journey with us. Thank you.
Wow, that was fantastic.
Thanks.
I can hear everybody applauding out there. That was such a fantastic and exciting and interesting talk. We do have some time for questions. And I see some already in the Q&A, so we'll go through those now. And I'd like to encourage anyone out there if you do have questions, go ahead and put them in the Q&A, and we'll take as many as we can in the time that we have. And first of all, thank you again. That was so interesting. I learned so much, and it was a really, really thrilling ride. I have a few questions myself, but I'll hold mine, and we can go through what some of the attendees' questions are first. The first question is from an anonymous attendee who was wondering about the graphic where you showed the L2 point, and they stated that it looked like L2 changes constantly as the Earth rotates around the sun. Does the JWST need to be maneuvered to maintain this position?
Yeah, that's an excellent question. I'm just trying to see if I could pull that up. just to have it for reference using the fancy navigation bar thing. Yes, so you're right. So what you're seeing is that it's not quite at L2, it's orbiting around this point in L2, and that does require some fuel to keep it in orbit. I mean, if it's like right at L2, it might be in the Earth's shadows, and do you want the solar arrays to get powered by the sun?
Okay, great. Let's see, the next question is about the testing of Hubble. So inadequate testing on Hubble allowed the spherical aberration to go unnoticed until after launch. What's been done with the JWST to ensure that any similar problems have been caught?
Yeah, that is such an excellent question. Of course, no one wants a repeat of what happened with Hubble, especially since we can't surface the telescope. So I will say that the testing for JWST has been extensive, much more extensive, I believe, than what Hubble went through. And some people might complain about the number of launch delays that have happened with JWST, and I could absolutely empathize with that frustration. But some of those launch delays are because testing revealed things that we needed to look at better to make sure that we do it right, and we do it right the first time. I'll also say that there have been a number of telescopes that have been launched that haven't been surfaced that have worked as intended. So having worked on the Chandra X-ray Observatory, sometimes like we would get a little bit snarky and say things like, well, unlike Hubble, we got it right the first time. And, you know, there's definitely are, and it's true, right? So there is a legacy of NASA launching telescopes that have operated as intended.
I'm going to sneak in one of my questions here, which is related to this question, which we of course all know it will not be serviceable at L2. But I had heard some talk at one point of maybe possibly creating a robotic servicing type of capability. I don't know if that's ever anything that folks have thought about more seriously should the need arise. You know, fingers crossed, hopefully it doesn't, but if it did, is that something that would possibly be on the table?
Yeah, so I've heard chatter, you know, about the space robots who could go up and service telescopes. I don't know that that's been explored in any depth at the moment for JWST. When I have heard it talked about, I think it was more in terms of future flagship missions. So I can't really speak to how much planning has gone into it, but I've heard the same types of ideas of, you know, robotic servicing missions can be the way of the future. And I think we are going to see probably more effort and thought about that, depending on what the results of the decadal survey end up being.
Mm-hmm. Okay, cool. Let's see, Jim is wondering, what is the biggest risk in the 180-day period getting to the science?
What is the biggest risk in the 180-day commissioning? Oh, man. I don't know what the biggest is. I mean, there are so many deployments, though there are some, I don't want to say redundancies. I think there are ways to work through things if something doesn't deploy quite as expected. And I'll also say some of the stuff that we've been doing at Space Telescope for the past year and a half or so are these rehearsal exercises. So the Mission Operation Control Center for JWST is going to be run out of Space Telescope. So once JWST launches, Space Telescope is going to be the hub for communicating with JWST. As part of those rehearsals are injected anomalies to practice the process of recovering and working through typical, maybe not typical, but things that you could imagine possibly going wrong, and how to identify what the anomaly is, how to fix it, and how to recover. Yeah, so there's just a number of things just between the deployments itself and just once we start turning on the instruments. I think I don't know what the biggest risk is, but I would be surprised if everything looked exactly as expected. I'm sure like once we get in-flight data and we start doing our flux calibrations, I am sure we're going to see that what we measured on the ground doesn't match what we see in flight by some like 5% or something, and we'll have to figure out how to calibrate that. So those are the things that I expect to happen more. Big risk items, I don't even want to think about it. I might end up getting nightmares.
Yeah, understood. Let's see, the next question is from Peter, who's asks if you think every star has at least one planet.
Does every star have at least one planet? I'm not sure if I would say every star, but it looks like many stars do. And many stars seem to have multiple planets. Yeah, so sometimes like people could get like a little bit cheeky in press releases. I remember there was one a bunch of years ago about realizing that there were, I forget how many more stars in the Milky Way galaxy, but the way that the press release was pitched was to say that means there's that many more planets in the Milky Way galaxy, and that means there's greater potential for life. So yeah, there's a lot of them out there.
Let's see, the next question is from an anonymous person who's saying, my understanding is that adaptive optics have allowed modern ground-based telescopes to achieve resolutions that now rival those of Hubble. Is there any chance that such technology could also catch up to JWST's capabilities?
Okay, yeah, so that's an excellent question. So adaptive optics is this really cool technique from the ground where you shoot up a laser guide star and you see how much this fake star gets refracted due to turbulence in the atmosphere. And you have mirrors that could correct for that. And then you can end up with these really crisp pictures from the ground. And adaptive optics does really, really great stuff. But getting above the atmosphere is always better. I don't want to say always. Most of the time, it is much, much better than what you could do from the ground. There are some limits to ground-based observing, even with adaptive optics. But it's also true, the next generation of ground-based observatories, we're talking about these 30-meter class mirrors compared with like an 8.5 meter in space. So you have much more collecting area. Another thing to also think about is that the atmosphere isn't transparent at every wavelength. So there are some wavelengths, especially in the infrared, where being on ground, you're just, even with adaptive optics, you're just not going to be able to observe certain wavelengths of light. So you really need to get above the atmosphere for that.
Great, thank you. Let's see, we've got a couple of people saying super interesting talk and thank you so much. There is a question about how many different filters will the different instruments be able to observe through?
How many different filters? Okay. Oh man, I don't know this off the top of my head. The answer is a lot, especially with NearCam. So let me get back to the slide of the various instruments. Right, so, okay, so NIRSpec, the near infrared spectrograph on the upper right, that does spectroscopy, so it doesn't necessarily have filters. It does have some ways of just chopping up the light, so either a spectrum through very specific chunks of the wavelength that at higher resolution, or you could observe a longer wavelength range with more resolution. But for filters, you're probably thinking more about imaging. And oh my gosh, I feel like, I mean, I could look this up. I don't want to do that while people are online. NearCam has probably, I don't know, maybe like 15 or 20. Nearest has, oh my God, and I'm the manager of Nearest, and I don't know the number off the top of my head. it's also probably it's less than NIRCam has. Probably I'd want to say maybe 10 to 15, and I'm not sure for MIRI. But it's a number, and there's a range of capabilities. There's some that have like a wider coverage, so you get more light, which is great. And then there's others that have less coverage to really hone in on specific features. In addition to the filters, there's other elements in the people and filter wheels of these instruments, so different dispersive elements to get spectra, or masks for coronography to block out the light from host stars. NIRISS has high contrast imaging using this really cool technique called aperture masking interferometry, which is this mask which turns the instrument into like an interferometer, so kind of like the way radio telescopes work. So the filters are just a part of what the really cool capabilities that JWST has.
Great. I'm going to combine the next two questions because they're somewhat related. John is wondering why French Guinea, and Susan is wondering if Nantucket, will the Nantucket sky be a visible sight to see the liftoff or the orbit at the beginning of the travels?
Okay, so those are both really good questions. So part of the reason French Guiana is a good spot for launching things into space is that it's near the equator. So it's it takes less whatever it is for orbital mechanics to get something up there. And whether or not it would be visible by eye in Nantucket, I'm not sure. Though I think there is a period of time shortly after launch where you might be able to observe JWST with the telescope, though I don't know for how long and at what how bright it is. Yeah. So I don't want to get people's hopes up, especially since the launch is supposed to be at 7:30 in the morning. So by the time it gets to be dark out, it's, you know, a bunch of hours later.
That's my homework, to look that up. Let's see. We'll just do a couple more questions so we don't go too far over. But Robert is wondering how they test the unfolding process. And there's a related question from Andy, wondering if JWST has been fully assembled or just specific assemblies. Are we counting on the cold and zero gravity of space as the exacting environment for success?
Okay, those are excellent questions. So JWST has been fully assembled. I believe it was in 2019, maybe October or November. So before that point, the sun shield and the spacecraft bus were at Northrop Grumman in California, and the telescope and the science instruments were being tested at various NASA centers. So started at Goddard, and then there was testing at Houston at the NASA Johnson Center, and then during Hurricane Harvey, there's like testing going on. It was it was kind of crazy hearing about everything, like major flooding, and people are like kind of camping out or trying to rent like SUVs to fly through to drive through floodwater to keep the testing schedule going. Like, people were dedicated to doing the testing. And then at that point, the telescope and the science instruments were sent to California, and there's some more testing that happened, and then they were combined. The full integration of the sun shield and the telescope and the instruments all came together sometime in late 2019. And then at that point was a large number of tests to make sure that all the different various components talk to each other. So they did several cases where they unfolded the membrane of the sun shield and folded it back up again. And they had basically special like pulley system set up to simulate the zero-G environment of space. But yeah, there's extensive testing to make sure that things opened and closed and then opened back up again and closed back up again.
Mm-hmm. Okay, awesome. Let's see, this is a good question that I'm curious about as well. A related question. Steven's wondering, where will we be with this 20 years from now? So I guess another question is, what's the expected lifetime of the mission?
Right. That's a good question. So I believe kind of like the nominal mission life is usually for these flagship missions, there's like the nominal lifetime of like about 5 years. And if things keep on working well, you go through NASA through a technical review to get approval to continue on for like another 3 years. I think like every 3 years there's a reapproval process. Right now, it's thought that the total mission lifetime would be about 10 years, somewhat limited by the fuel to keep it in its orbit around L2. But maybe it could go longer. We'll see.
Okay, awesome. And actually, a related question just came in from my dad, Wilbur, who was asking, what is the propulsion fuel to cross that 1,000,000-mile distance? And I'm just asking that because you just mentioned the fuel.
Yeah,
if you happen to know.
I don't know. It's
Okay.
a good question. I should look that up.
But I guess some of the energy, you also said it has solar arrays. So some of the energy to get out there will be perhaps the solar as well, or?
So I think the solar might just be for like powering the science instruments.
Okay.
And the guider.
Okay.
I think for propulsion, it's whatever the fuel is that I'm not sure.
Okay, no worries. Awesome. Let's see. We've Peter Boyce is saying thank you. Perhaps the best popular talk he has ever heard.
Well, thank you so much. That means a lot.
Great. We have one quite specific science question from Jim, who's wondering what's the resolution for NIRSpec?
What's the resolution for NIRSpec? It depends. There are different gradients and different settings that an observer can choose. So there's a range of something like maybe a resolution of like 100 to 200 to maybe up to several thousand. I forget the exact numbers, but it's a range based on the observer's choice.
Yeah. Awesome. Okay, we have one last question. I'll combine the two last questions. Lots of folks are saying thanks so much, very informative talk. And this question is about how fast does JWST travel on its way to L2? And I'll combine that with someone else said L2 doesn't seem too far away. Why couldn't it be serviced in the future?
Okay. All right. So that's a good question of how. So I'm embarrassed that I don't know how fast JWST is traveling on its way to L2 because there was much chatter about this recently at work. On one of the Slack channels. We had an all hands meeting yesterday, and one of the topics was about JWST, and people were asking about this type of stuff, like, well, when does it pass the moon? And this is why I added to my talk this morning, because like we got the answer. This is where someone looked it up and posted on one of the Slack channels. I'm like, oh, that's so exciting! I got to add that in. And there was talk about how fast it travels, but I don't remember the numbers.
Okay, no worries.
And L2 not being that far away, why can't it be serviced? But we haven't really sent astronauts out that far. So if it was to be serviced, it would have to be through space robots, and that's not something that NASA has invested money into investigating at this point. But I think that will end up being the way of the future with the next generation of flagship missions.
Mm-hmm. Awesome. We got through all the questions. There were lots of, thank you so much. This was a fantastic talk, and I will just add mine. This was really so informative and so exciting and so interesting, and to hear from someone who is on the ground working day to day on this is just so exciting. So on behalf of all of Mariah Mitchell Association, I just want to thank you so much for your time. And to everybody who tuned in tonight, thank you for being here. If you missed anything or you'd like to rewatch it or share it with your friends, we will be posting the recording of the talk on our YouTube channel tomorrow and or the next day. And I guess with that, we will sign off for tonight. And thank you again, Stephanie. This was such a fantastic talk, and we really appreciate it.
Well, thank you all for having me, and thanks for coming out to listen about JWST. It's an honor.
We will be all anxiously watching on December 18th with our fingers and toes crossed too, following up on all the progress.
Excellent. Thank you.
Thanks so much. Good night.
Night.